In the last lecture, we were discussing surface tension. In particular, we discussed the angle of contact, and we found that if the angle of contact is less than 90 degrees, it is acute, then the liquid will wet the solid surface. If the angle of contact is more than 90 degrees, then the liquid will not wet the surface of the solid. And this wettability is important from the point of view, say, in our daily lives, from the point of view of cleaning clothes. If the water is not able to wet the surface of clothes, then it won't be able to remove the dirt. So, therefore, we add detergents which reduce surface tension and also reduce the angle of contact, so that the water spreads over the surface and is able to clean the soiled areas. In this lecture, we take some other properties of fluids. We will talk of streamline flow and we will talk of the important Bernoulli's principle. If you have ever stood on the bank of a large river, say like Ganga or Yamuna in plain areas, you will see the water flows very slowly, very placidly, very orderly. There is it's a very orderly flow of water. On the other hand, if you ever stood on the banks of a river far from its source, that is in the plains, say a large river like Ganga or Jamuna, you must have noticed that the water flows very placidly, very quietly and very orderly. If you choose a point, at that point the velocity of flow is constant. Such flow is called streamline flow. On the other hand, if you see stream or a river or water in a channel which is, say, during floods, then you will see that water does not flow quietly, does not flow orderly. There are, let us say, things like these irregularities and these eddies in water. The water does not flow quietly, but it flows like this, and if there is some obstruction, then it flows over it, and there are eddies like this produced in water. And if you concentrate on a point, then at that point the velocity is not constant. Velocity of flow is not constant. The direction of flow is also not constant. It keeps changing every second. Such a flow is not a streamline flow. I will give you an example, very interesting example. If you have visited, say, some place higher up in Himalayas, you must have seen a river or a stream there. I have a picture of river Ganga in the Himalayas, and you see the water flowing not very quietly, not very orderly, and it has a very sort of, there are eddies if there is an obstruction and so on. This kind of flow is not a streamline flow. The streamline flow is this, where it is very steady, and if you concentrate at a point, then the direction of flow of water and the velocity of flow of water is constant. Now, these are again streamlines. How do you define a streamline? A streamline is shown here, a blue curve, and the tangent to it gives the direction of flow of water. And if a small object, say a piece of wood, is placed into water flowing steadily, the path traced out by the object is called a streamline. That means, if you want to see what a streamline looks like, you stand at the bank of a large canal, say, just float a paper boat, and then you see the direction that it takes. You will see it will flow steadily in the same direction, and the path it traces is called a streamline. And I show streamlines here, and the tangent to a streamline at a point gives the direction of flow of water. Here again two more examples of streamlines. Take this streamline for example. Here the tangent to this is in this direction, so this is the direction of flow. Here the tangent is in this direction, therefore, this is the direction of flow of water. The concept of streamlines is similar to the concept of lines of force in electric field or magnetic field. Let us take an electric field. This is the line of force. Tangent to it gives us the direction of the field. In a streamline, similar thing happens. The tangent to the streamline at a point gives the direction of flow. As two lines of force cannot cross each other, because we must have a unique direction of the field at that point. Similarly, two streamlines also do not cross, because at a given point you cannot have two directions of flow. You must have a unique direction of flow at that point. So, therefore, two streamlines do not cross each other. I show you two more examples of streamlines. Suppose water is flowing and we have a cylindrical object in its path. Then what happens? The water will flow over it, just as here. This is a cylinder and water flows over it orderly in streamlines, if the flow is not at very high speeds. Here is an important thing called aerofoil or airfoil, and if this is in the way of the fluid flow, then the streamlines will take this shape. They will go over it and they will go under it, but they will remain streamlines. The motion of the fluid is said to be turbulent when it is highly unsteady, as I showed you the example of the river Ganga somewhere near its source. You see, here water flows chaotically. I mean, at a given point the direction of flow changes, the velocity of flow changes, and if there is some obstacle, then eddies are produced inside this water. This flow is called turbulent flow, and turbulent flow is very difficult to understand mathematically, at least at this stage. How does turbulent flow come in? Here you have the streamlines, as I showed you earlier also. This is a cylinder, the water flows over it and water flows under it and flows along streamlines. This is slow fluid motion. But suppose the fluid motion becomes fast, then what happens? Then you start seeing these eddies behind the cylinder. You will start seeing these eddies. This is the beginning of the turbulent flow. And if the velocity of the fluid increases more further, then you will see more of such eddies. The turbulent flow has become more turbulent as the velocity increases. What decides whether the flow would be turbulent or streamline? There is a number called Reynolds number, which decides whether the flow would be streamline flow or would be turbulent flow. And this number is given by this expression, rho V L by eta. Rho is the density of the fluid, V is the velocity, typical velocity of the fluid, and L typical dimension of the channel in which the flow takes place, and eta is something that I will explain further also, is something called the viscosity of the fluid or viscosity of the liquid, and this number is dimensionless. If you plug in the dimensions of rho, V, L and eta, you will find that this has no dimensions, this is just a pure number. So, this is the streamline flow. In the case of water, this Reynolds number must be less than or about 2000. If this is less than 2000, then the flow is streamline, as shown here. There is no turbulence, you can see there are no eddies, there is no irregularity. On the other hand, when the number Reynolds number goes beyond 2000, then flow starts becoming turbulent. I mean, it starts, becomes irregular. And when R is greater than about 4000, then the complete turbulence comes about. Water flow is completely turbulent. So, let us see the situations where this R will give us turbulent or streamline flow. First, Reynolds number is a dimensionless number, as I already explained. Less viscous liquid, viscosity of liquid is like resistance, something like resistance, we will explain in a moment. So, less viscous liquids are more likely to become turbulent. You see, eta is in the denominator. So, if eta is smaller, then R increases. That means the possibility of turbulent flow increases. Flow in broad channels is more likely to become turbulent, because the radius or the cross section of the channel is in the numerator. So, if L increases, R tends to increase, and therefore, the probability of flow becoming turbulent is higher. As long as Reynolds number is below about 2000, the flow of water remains streamline flow. What happens if the flow is streamline? You see, when water flows through a channel, say a pipe or a tube, then the attraction between molecules of the substance of the channel and water molecules, and then the interaction between water molecules further off the walls, all this results in the resistance to the flow of water in each layer. So, what happens is that near the wall the resistance is so much that there is almost zero velocity, very small velocity. If you observe this, you will see that water along the walls is flowing very slowly, and this velocity increases and becomes maximum in the middle of the channel. The velocity increases gradually, and the layer along the axis moves fastest. The forces between molecules in adjoining layers of the fluid produce friction between layers of the fluid, which results in the resistance of the fluid to flow. So, the result is that near this wall the flow has very small velocity, near this wall of the tube the flow has very small velocity, and it increases, and obviously along the axis the flow is with the largest velocity. And this resistance to flow, say this layer is being affected by molecules above and below, they cause resistance, and the resistance to flow is called viscosity. Now, since there is a resistance to flow, we must apply a force to make water flow through a pipe or through a tube. Let us look at this picture. As we go away from the wall, then the velocity increases. That means there is a velocity gradient, dV by dy, there is a velocity gradient, and the force that we need to apply to make water flow in a streamline flow through a pipe or a tube is F equal to the area of cross section of the tube into the velocity gradient and into a constant eta. This constant eta is called the coefficient of viscosity of the fluid. This determines the force that needs to be applied to make the flow overcome resistance and flow. From the formula for eta, the units of viscosity are found to be Newton second by meter square or kilogram by meter seconds. There is no special name for any unit in SI system. However, people use a unit called poise, and 1 poise is 1/10 of Newton second per meter square. In addition to eta, we also have what is known as kinematic viscosity, which is eta by rho. You divide by the density, and the viscous flow, where velocity of the fluid increases towards the axis of the pipe or tube, is also known as laminar flow. Flow in, see, like a laminate, this is laminar flow, and I show you again the flow is streamline, the velocity increases as we go towards the axis. That means the velocity profile has this shape, and the liquid flows through the pipe. This flow, in which the flow is streamline flow, is called laminar flow. Now, suppose we have laminar flow, then what happens? A spherical body of radius r is moving through it with not too large a velocity, I mean with a small velocity. The viscous resistance or viscous drag experienced by it is given by Stokes' law. You see, suppose we have air in this, say a small ball of lead, let us say, is allowed to fall, then this ball will experience resistance of the fluid, in this case air, and this is the force, that force of resistance exerted on this ball is given by Stokes' law, and this force is called drag force, Fd equal to 6 pi eta Rv, where eta is the familiar viscosity, r is the radius of the ball, and v is the velocity with which the ball is falling in air or in any other liquid. Now, suppose the body is falling in air, neglecting buoyancy due to, you see, if a body falls into a liquid, then there is a force of buoyancy acting upwards. We can neglect, in the case of air, the force of buoyancy. Then the net force acting on the body is its weight mg minus the force which is upwards, which is 6 pi eta Rv. So, the net force is 4 pi by 3 pi r cubed rho g. This is the volume times density times g, that is the weight, and 6 pi eta Rv, that is the force given by Stokes' law, which opposes the motion of this body. If we equate these two, then the velocity, you see, if these two forces become equal, then there is no force acting on a dropping, say, ball or even raindrop. There is no force acting on it, and therefore, since there is no force, there is no acceleration, therefore, the velocity becomes constant, and this constant velocity is called terminal velocity. You see, you have a raindrop coming from a great height, and then at some stage the weight is balanced by the force of viscosity or force due to viscosity given by Stokes' law. At that point, there is no net force acting on the raindrop, and therefore, it acquires what is known as terminal velocity. After that point, it falls with constant velocity, terminal velocity. And if we just use this formula to derive the expression for V by equating these two, and V terminal is 2 rho g by 9 eta times r squared. Notice that it is proportional to r squared, and we shall see very interesting consequence of this, is proportional to r square. Because of their long journey, raindrops and hails are bigger pieces of water falling, are able to acquire terminal velocity. Then they fall with constant velocity. Since the terminal velocity is proportional to r squared, larger and heavier hail pieces, they fall faster. Remember, according to Newton's law, every object must fall with the same acceleration. Here we find something different. The larger pieces fall faster than the smaller pieces. It is all because of viscosity, and these larger pieces, they acquire larger velocity, larger kinetic energy when they suppose hit you, and therefore, they can cause greater damage. So, if you are going outside in rain, and rain drops will not harm you, but if there is a hailstorm, hails falling can cause lot of injury, because hails being larger in size, they acquire larger terminal velocity and larger kinetic energy, because the terminal velocity is proportional to r square, and therefore, these hail pieces, they fall faster than the smaller and lighter ones, making them potentially more dangerous if they hit you. When a body falls in a liquid, say a steel ball falling in a liquid column, then force of buoyancy cannot be neglected. Then what happens is, the drag force as well as the force of buoyancy, they act upwards, the weight of the ball acts downwards, and when these two are equal, the upward force and the downward force, then the ball acquires terminal velocity. And the equation now is this: the F net, the net force acting on the ball is 4 by 3 pi r cubed into g into rho b minus rho l. Rho b is the density of the ball, rho l is the density of the fluid, and this 4 by 3 pi r cubed rho l into g gives the force of buoyancy. This is equal to the weight of the liquid displaced, and this is the weight of the ball itself, and this is the Stokes' law, the force due to the viscous drag. And when F net is 0, then we get the terminal velocity, and the expression now is 2 r squared into g by 9 times eta into rho b minus rho l. So, if you have a small ball of steel falling in a long column of mercury, say in a burette, then you can see that it falls, it has an acceleration, but after some time it falls with constant velocity, because the net force acting on it becomes 0, and after that the velocity becomes constant. In this lecture, we have discussed some properties of fluid like the viscosity, streamline flow, turbulent flow, and the terminal velocity which is acquired when a particle falls through a long column of a liquid. Next time we shall take some more properties of liquids. We shall discuss Bernoulli's theorem. We shall also discuss Torricelli's law and some other phenomena.